Testing. Good. Okay, well, thank you very much for thank you for the comment, introduction, Dan. I am stepping in for Bob Hallberg, who is a federal employee and therefore unable to work because of the shutdown. Needless to say, we're living in interesting times. This is going to be a talk, a lot of equations, I'm afraid, and this is why it's great that we're starting 5 minutes early, because we're going to be working hard. This is not normally the material I would present. This is the material Bob would normally present. So you'll have to forgive me when I make mistakes and get stuck. But nevertheless, let's get started. First of all, just give you a quick history of MOM6, because MOM6 goes all the way back to the famous Cox and Bryan code. Has anyone here not heard of the Cox and Bryan code? Probably a lot of you. Actually, there we are. Okay, so Cox and Bryan was the first global ocean model that was going to then be part of a couple model all the way back in the, actually I thought it was even earlier than the 80s when they first started working on the code, but it was published in 84, and it's the foundations of this whole lineage of global ocean circulation models known as the MOM series. But it wasn't called MOM in those days, it was named MOM by I think Tony Rosati and others around in the early 90s. And as you can see, there have been multiple versions. And those versions were basically mostly refinements in code, and in particular in the way that they're actually put onto computers, because the computing in those days was changing. You know, they started from kind of, well, I forget what they were called in those days, but kind of scalar computing to vector computing to massively parallel distributed SIMD type machines and so on. So the computing kept on changing, so there are new versions of code needed. POP, which is the model that was used here at NCAR, was a version that was taken and basically refactored for the computing by NCAR and Los Alamos. And I forget when was that, Frank? What year was that? It's around the early 90s, right? Late 90s too, okay, yeah. Anyway, so there's been a series of MOM, and most of that was mostly about the computing with new physics, new parameterizations being added, refactorings of the code. But at GFDL, in the early 2000s, this is around the time I arrived, Bob Hallberg convinced me to not work on MOM directly. I worked on it a little bit, but to think about trying out new algorithms. And so we, in parallel, started this other project where we're looking to see whether we could change the way that we were solving the equations of motion. And we developed this model called GOLD, and that led to a comparison between two models in 2012, 2013. Was the publication of a parallel set of models, ESM2G and ESM2M. And the G stands for gold and the M stands for MOM. And that comparison was about whether there was advantages in using an isopycnal framework to describe all the physics and the dynamics, or to stay with the way that we've been doing it in MOM in height coordinates, geopotential coordinates. And that comparison convinced us that we needed to change our framework and focus on a more general approach. So in 2013, we started MOM6, and we were trying to carry forward the community, but clearly a whole new algorithm. It was a whole new code at that point. And so that started in 2013. I can't do my math. 27 years. 4 years later, NCAR makes a fork of MOM6. So the fact that they did that is sort of a testament to the value in these new algorithms. This only goes to 2019. A lot has happened since then, and one of them is that there's been application of this global scale model to regional projects. We've been doing it also at GFDL in collaboration with Rutgers and Alaska Fairbanks with Kate. Then there's also the biogeochemistry and the data assimilation, all the other things have been happening, and that's all been happening in more recent years, but that's not on the graph. So a quick outline. As I said, there's going to be equations. So we're going to spend a few slides talking about equations. I'll try not to rush too quickly, but you also don't need to remember them too much. And then we're going to talk more about the code, about how we do this, how we solve these equations, both in terms of algorithms, time stepping, and spatial discretization. And the only thing I would normally talk about, and the only place where I would normally have not equations but figures, is in the vertical coordinates and remapping description, which is the stuff I normally talk about, but somehow Andrew got to talk about that. So I had no material whatsoever to start with. So Andrew's talking about that later, so I've tried to not use all of that stuff. And then I will briefly introduce the open boundary conditions. I see that Kate and Fred are also going to be talking about this in more detail. Okay, and then just one pointer is there is documentation. And in fact, again, we have to thank Kate for that. Kate wrote most of the documentation. It's at MOM6 readthedocs.io and is, I would say, what, 80, 95% there. I mean, it has gaps, but it also, most of the content I'm going to show here is actually on that website. And when this particular talk was given in 22 by Griffiths at a Princeton tutorial, he literally just went through the website. I'm not doing that to you. Okay, so we're going to talk about the equations, and I'm going to start off with the Navier-Stokes equations. Hands up who does not know what the Navier-Stokes equations are. Okay, hands up who knows what the Navier-Stokes equations are. Hands up who's willing to explain what the Navier-Stokes equations are. Okay. They are the equations that that describe and govern the evolution of fluids. Not necessarily only limited to Newtonian fluids, but let's just keep it simple. And this includes the fluid dynamics of the ocean. The Navier-Stokes equations are formed from momentum equations in 3 dimensions. And so here, the notation I'm using is that I should use my mouse, right, so that I would use my mouse, but there it is. No, it's not. There it is. Okay, good. This is useless. So this V, when I'm using V, I'm referring to the 3-dimensional velocity. And when I use the little u, when I use u, vector u, I'm referring to the horizontal only component of that 3-dimensional. And the reason for that is, as you'll see in a moment in the next slide, because we generally don't actually use the vertical momentum equation. And then, so we've got the momentum equations. They're driven by pressure gradients, stresses, and also geopotential gradients, which is the phi. And then we have a continuity equation, which is a conservation of mass. That's the d rho dt term, second equation. And that just says if I have mass moving together, I get denser. And if I have mass pulling apart in divergence form, divergence of fluxes, I get lighter. And then we have a conservation of heat, which is written in terms of a potential or conservative temperature, theta instead of temperature. That's taking out the sort of compressibility part, salinity, and then we also need an equation of state. So this is the Navier-Stokes equations for the ocean, but we don't solve these equations. Can anyone tell me why? Any guesses? It is chaotic, but that's not the reason we don't use the Navier-Stokes equations. Okay, so what are we interested in when we're working on global scales? What sort of time scales and velocities are we looking at? Typically, well, I'll give you a clue. The typical velocity scales in the ocean of order a meter a second. Gravity wave speeds, in terms of surface gravity waves of order, maybe hundreds of meters a second. But there's one faster. There's one mode that's faster than that, which is, it's how you're hearing me right now, sound. So the Navier-Stokes equations contain sound waves, commit sound waves, sorry, and they travel at 1,500 meters a second in the ocean. The ocean's fairly incompressible, sound travels very fast. And these terms I've highlighted in red are the terms which are responsible for giving us those sound waves. And this is, if we were resolving those sound waves, if we had an explicit system, we had to resolve them, it would make our time step prohibitively small, too small. And the sound waves are such low amplitude features in the system of no interest to anything that we're doing at global scales, and not even at regional scales, I think. Certainly, yeah, I'm certainly not certain that's the case. That we don't want to resolve them, we want to filter them out. And it turns out you can filter them out several different ways. There's 2 primary ways that we do it. And in general, for the most part, we've done it both ways. So remember, these 4 terms I've highlighted are what you need to get sound waves. So if you intercept the equations, if you make changes in at several of those places, you'll be able to get the sound waves. So the 2 main approximations that we've traditionally used in the ocean are to make the system hydrostatic. So that means that in the vertical direction, we no longer have an acceleration term. We just have a balance between gravity acting on buoyancy anomalies and the vertical pressure gradient. That's hydrostatic balance. And then the other one is the Boussinesq approximation. The Boussinesq approximation is interesting because it is the, if I go back to the previous slide, it is changing that continuity equation. And that's actually one of the critical equations for propagation, the propagation part of sound waves. So the Boussinesq approximation, an easy way of saying it is that wherever you see a density, you replace it with a reference density, except when it's multiplying the geopotential. It's not actually as simple as that, and in particular, for consistency, you have to replace the pressure in the equation of state if they're going to be Boussinesq, something that a lot of people forget. So there are two ways to filter, and the reason I'm making this point is MOM6 now actually has a non-Boussinesq formulation, and I'm not going to talk about it any more than on this slide because I think at global scales it can matter because we want to have true mass conservation for things like sea level change. But at regional scales, I think the time scales are fast enough that you won't really be worrying about that. So I imagine they'll be using the Boussinesq approximation fairly safely in regional scales. But it turns out the hydrostatic balance also filters out sound waves in the vertical, and it leaves just one horizontal propagating sound wave, which oddly doesn't seem to actually manifest itself when you actually do this. So it's possible to write down just the hydrostatic non-Boussinesq equations and not have to worry about sound waves. Okay, so that's why we're not using the non-Boussinesq and non-hydrostatic equations, which are the Navier-Stokes. So these are the equations which we're essentially trying to solve. We'll limit ourselves to Boussinesq today. Always hydrostatic. MOM6 is always hydrostatic, at least for now. There's one other common thing or something that we've done in MOM6, which is not necessarily common to other models, although we did do it in the MIT model, and that's to write the equations in a very particular form. And to me, it's just much more elegant this way. If you were to take the equations of motion, which I just had on the screen, there's a total derivative of velocity here in the momentum equations. And if you look at that operator on the sphere, first of all, or in curvilinear coordinates, you get all these metric terms because it's the total derivative of this vector quantity. And those vectors are changing either on the sphere or when you're rotating. But there's an identity that lets us rewrite that total derivative. I've expanded out there on that first line. And then I've just rearranged a few terms to write it as a local acceleration, d by dt, this is horizontal only, u, times an vorticity across that horizontal flow, plus a vertical advection of a shear, and then a gradient of kinetic energy. And it turns out this is what we call the vector invariant form of that operator. It's vector invariant because it doesn't have any metric terms when you work in these curvilinear coordinates. So this is now the new momentum equation down here at the bottom, and it doesn't have that big total derivative. It's the vector invariant from the momentum equations, and means that we only have to discretize it once and not worry about all these new terms that appear like tan phi's and u over w's and all sorts of other things going on. So this is why we do it. It's simpler, and it also lets us interpret what's going on in the equations. So here we are. This is the final set of equations in z coordinates that we're trying to solve. I've highlighted the vector invariant transition there. So we have an advection of absolute vorticity, which is, so you can think of the Coriolis term as a transport of absolute vorticity. That's why I like this one, because you can interpret it that way. We have hydrostatic balance, we have non-divergence, and then we have heat and salt, and an equation of state written with a kind of reference pressure. Okay, so there we are for the equations in z coordinates, but MOM6 is known for being a general coordinate model. So what we're now going to do is we're going to do a transformation of these equations into a general coordinate. And for some reason, we use the symbol R. And I can't say my R's, so just don't laugh. Just don't laugh at me. But we use R as the coordinate in these equations. And when we do that transformation, we need to have a metric that converts Z to R, and that's this specific thickness, the ZdR, which I've written here, and it's the so you'll see this appearing in the equations. And then in this new coordinate R, it's just an arbitrary function at this point. We also have now an R dot, which is the cross-coordinate flow in these equations. Now, if I compare these equations in R coordinates to the previous equations, I was flipped back and forth a few times, you'll see that the form of the equations is basically the same. All that's happened is that we're introducing this kind of specific thickness to ZDR in a few places inside the derivatives and inside the transports, okay? So ostensibly, the form of the equation is the same, but we're now actually in general coordinates. And in particular, you'll see that all these horizontal gradients are now measured along surfaces of constant R. But this is the actual equations which we're trying to discretize. And so this is the general coordinate equations. This is where we start from, where we start with the discretizations, and now we'll actually talk about the discretizations. But is there anything ambiguous, or any questions about the equations so far? We've gone through hydrostatic, balance, we're saying Bose and S for the time being, and we're now in general coordinates. Yes.
So does this like general coordinate transform conserve like heats
Yeah.
and mass in this general coordinate, or does it conserve it across?
It does. It conserves heat because we didn't make any new approximations apart from the smoothness of the coordinate. In fact, that's hidden. But we didn't make any approximation to these equations when we did the transformation from this equation where we're conserving heat through the potential temperature equation and salt. We didn't change anything. We just, the transformation introduces the specific thickness. So there's the ZDR times theta. So that's saying that we're going to, in this coordinate system, you have to say how much stuff is there, ZDR, times the stuff you're measuring, which is the theta. So this is a conservative equation. One thing I forgot to say is I much prefer to write the equations in flux form like this, rather than in terms of total derivatives. I started out without total derivatives in my equations. I'm not preserving temperature as I move around with a fluid parcel. I'm thinking of boxes, and it's about fluxes going in and out. That's a personal preference. This is how I like to think. So this is now conservative equations for the total amount of stuff between surfaces, horizontal fluxes along those coordinate surfaces, and of course, cross-coordinate part. Thank you. Right, so vertical discretization. So we had these equations, and now we're going to discretize them. And all we have to do to discretize in the vertical now is we're going to integrate between two surfaces of constant R. I haven't told you what R is, but I'm just, we're just going to do that. We can say we're going to take one value of R, we're going to integrate these equations up to another version of R. And so, just as for reference, if I take my ZDR, my specific thickness, and I integrate it between two surfaces, what I'm going to have is the distance between those surfaces, and we're going to label that H for thickness. And then the equations down here are now integrated in the vertical. So these are discretized. They're still written down as continuous in the horizontal, but that delta R symbol, that means a difference in that direction, okay? So +1, -1 in that direction. So this is like a delta in the vertical. And so these are now discretized in the vertical. And for reference, when it comes to looking at the code and in papers and equations, we have a convention of indexing the model in the vertical starting at the top. So the top layer of the model is labeled 1, bottom layer is labeled NK, and we use a half index for the interfaces. And we like to use the half at the top and have the K minus half above the K layer. It's just a convention. But the equations now, simply by integrating over this between the two surfaces of R, have produced these equations. And those equations, with that H in them, are actually very reminiscent of another set of equations, which are these equations. All I've done here is I've blanked out some terms, which are the vertical motion terms, okay? So there's the similarity between the full equations in R coordinates, but integrated, and these equations is actually what dictates the algorithm to us, because these are the stacked shallow water equations, which are a famous set of equations used for studying dynamics. Very much simpler to think about in terms of these inviscid layers that don't mix and they interact with each other through pressure influences of pressure between the layers. These equations are actually a little bit more general than that because I've included density as a variable, but in principle, if you make the density constant along these layers, these are the stacked shallow water equations. So that similarity between the full equations and these equations is, the best way to think about how the algorithm is working. is to think about it as a series of stacked shallow water equations, even if your R coordinate is not an isopycnal orbit or Lagrangian. For example, this algorithm still works in Z coordinates, and we'll talk about this in a minute. And Andrew's going to talk about it even more later. Is he today or tomorrow? Tomorrow, okay. But the other reason I've blanked these equations out is to get you into how we're actually going to build the algorithm, which is because of that similarity, if we could zero out these equations, zero out these terms with the R dots, so the terms I removed are these R dots. If I could zero them out, I do get these equations, I could use a solver that is solving these equations. And that's actually part of how we do the algorithm. What we do is as we're marching forward in time, we hold the properties in R constant. We have a zero R dot for a finite amount of time, and that allows the system to move around Lagrangianly. And then we say, okay, now we're going to be, our coordinate system, our coordinates positions have moved around inconveniently, so we're going to actually change them by doing a remapping. And so this is actually the heart of the algorithm. Now I want to talk about a few terms in these coordinates, and in particular, the pressure gradient is a nasty one. So if you, I've drawn here on the right-hand side a sort of schematic of one of these layers between two R surfaces. My R surfaces are kind of wiggling around. They're not Z-coordinate, they're not flat. They're wriggling around. And I've got this layer of fluid. I've got two parcels of, or two cells, you could imagine, a red cell and a blue cell, and their mean positions at different heights. And they're going to have different pressures and different densities. And the kind of shading is kind of an interpolation of density between those two. And if you look at the equations we've got in general coordinates, I have to measure a horizontal pressure gradient along the R surface of P, and I have to also measure a horizontal gradient of phi, the geopotential. And geopotential is just a G times Z times the density. So I've labeled that here, kind of schematically trying to show you that by having the center of those layers inclined, I have to measure a delta P in the vertical and a delta phi in the vertical times a rho, which I'm going to have to figure out how to interpret. And over here, I've just written down a discretization. I'm going to use the average density between the red and the blue bits, multiplied by the delta of phi. The delta x means difference in the horizontal direction. And the problem with that is that when you look at those terms, for the most part, in fact, always, will have opposite signs because there is a strong component of gravity pointing downward. And one way to realize this is phi is a quantity that's always increasing upward because it's GZ, right? Geopotential energy, if you have something up here, it's got more potential energy than down here, right? So GZ increases upward, but pressure increases downward. So when I look at the delta phi and delta P, they have opposite signs. In this particular scenario, delta P is negative and delta phi is positive. Okay, so they are always going to be opposite sign, which means that there's this part that is always trying to compensate for each other. And this turns out to be a classic source of error in general coordinates. And there's been something that has, for decades, many decades, has been a bane for models which are not using simple coordinates. One contribution to that we made in MOM6 is to try to turn it to not use differences in that sense I just showed you, but to actually rearrange things into integrals. So that term, those two terms, d by dx along an R surface, actually came from the horizontal gradient along a Z surface. And the reason this is relevant is that U is still normal to the vertical. So even though we're in R coordinates, there is no orthogonality between the general coordinate R and the vertical. So we're not doing three-dimensional orthogonal coordinates here. We're doing non-orthogonal coordinates between the vertical and the horizontal. So with the thing we're trying to calculate accelerations for is the horizontal motion, not the motion along the surface. And this is one of those weird things that takes a lot of thinking and getting used to. But the equations we're trying to solve are for the horizontal motion, which means we're trying to measure the horizontal pressure gradient. And if I take that horizontal pressure gradient and integrate it over a volume, which I've indicated here around a U point, so the red dot and the blue dot are kind of the centers of temperature points, and the volume I've indicated is kind of a volume you might interpolate for the velocity point between it, and we'll talk about staggering later, then I can turn that dx dp along a z surface into a line integral of pressure dz. That's just, oh my goodness, which math theorem is it? Divergence rule, right? What's his name? I'm sorry, I'm drawing a blank. I'm getting old. This relationship, okay, you can turn an area integral into a line integral, right? When you have an area integral or divergence gets turned into a line integral. So we just need to measure the pressure drops, the pressure along these changes in dz. And one thing that you can just see, if we were doing a z-coordinate model, those dz's would be 0 for the top and bottom surface, right? So if r was set to z, you would get no contribution from the top and bottom. You'd only be looking at the average pressure change along the two sides. So this is why this is kind of gives you some natural limits when you look at some certain coordinates. So this is a different way of doing that discretization. And we found, oh, where's my slides? Can I just see if I seem to have lost a slide. I'm sorry, it's over here. Let me just, for some reason, out of order. Don't know how that happened. So that pressure, using that approach, we can show that first of all, those line integrals in the paper where we wrote this up, we actually took the nonlinear equation of state and we analytically integrated it so that there was no numerical approximation. And when we evaluate that for stratifications which are representable by the reconstructions that we use in the model, then we can show that we get perfect dynamics. There's no pressure gradient error. That's not to be misunderstood as the model not having pressure gradient errors, because in general, your stratification is not going to be perfectly modeled by your reconstructions. There's always going to be a bit of error. So when I say reconstructions, I'm talking about trying to do interpolate fields between data points. But over here is a plot from plot. This is a standard test that was used in regional models that use terrain following coordinates. Can you set up your model and have it stay stationary for simple stratifications, flat stratifications with topography? And most models have a lot of trouble not having what we call spontaneous motion. And so we were able to show that up to some order, depending on the reconstructions, we were able to maintain no motion. We've now generalized this approach to use numerical quadrature, so we don't have to do analytic integrals of these nasty equations of state, especially with the new equations of state, which have 47 polynomial terms. No one's going to sit and do those by hand, so we now use quadrature to do those numerical evaluations. Okay, so back to the order of, so I was here, I think. I'm having trouble with this. I was here. So we've dealt with the pressure gradient. That's discretization. So I think we've now handled most of the discretization in the vertical. We've now discretized these general coordinate equations in the vertical. We have a pressure gradient term that's done by finite volume integrals. So now we can talk about the algorithm. When did I start? 9:30, right? Yep. So this is a schematic of our algorithm, and I have kind of symbolically put our equations here. These equations are slightly different to what we had. But on the top here, I've got the first three equations are the pressure integral written as a delta, even though we're doing finite volume. The horizontal momentum equation with pressure gradients and geopotential gradients with a time step delta t, and a thickness equation, which is the continuous equation. Those three equations were part of the system which you saw earlier. And then lower down are here, C is a general form for the temperature or the salinity equation. So this C is a scalar, and this is our basically where we're going to step forward temperature and salt. The blue equations at the top, remember I said that these were stacked shallow water equations? Those stacked shallow water equations, without worrying about temperature, salinity, or anything else, describe internal gravity waves whose speed is of order, anyone? I'm not sure actually. Is it 5 meters a second, 10 meters a second? Who's an oceanographer here? Make a guess.
Order one. Order one. Yes. Thank you.
Is larger than one exactly, because velocities of order one, and we don't have supercritical flows in the ocean mostly, but yeah. So we have these internal gravity waves described by these stacked shallow water equations, what we're going to refer to as the baroclinic equations, which model the internal gravity waves. And so we're going to use that as our kind of primary time step. In the code, you'll see this as delta t, dt, sorry. And here it's delta t. Now, unfortunately, we've already got rid of the sound waves, but we actually also have very fast modes still left behind, which is the barotropic modes. And so that's the evolution, the gravity waves controlling the sea surface. That's the fast modes. And those are of order hundreds of meters a second. And they travel, root GH. Root GH is of order 100 meters a second. And those equations can be obtained by vertically averaging or integrating the barotropic equations and then just saying what's the part that depends on the vertical average flow and the sea surface. So those equations, they need a much smaller time step. So what we're actually going to do is we're going to have a kind of guess at these big blue equations. Before finalizing them, we will subcycle, it's called subcycling. We'll integrate forward these light blue equations with a smaller time step. And then we'll do some sort of back substitution so that allows us to actually step forward the big blue equations with the terms you would associated with the little blue equations. So that's what we call for the kind of the split algorithm, where we have baroclinic and barotropic equations being integrated with different time steps. The reason we do this is we often might have, say, 50, 70, or even hundreds of layers. And if you're using a time step dictated by the barotropic mode, your model now becomes 100 times more expensive because with your small time step. Whereas by separating this out, you can spend time solving that barotropic part with that small time step, and then you can take your longer time step with the bigger part of the model, okay? So this is a big time saver. But we haven't yet changed temperature and salinity. And on this graph, you'll see that we can actually take a longer time step there. And that's because the system is Lagrangian in the vertical, we are actually just moving, as the layers move around with these gravity waves passing through, we're just carrying heat and salt up and down, and not actually doing much else. In the z-coordinate equations, the gravity wave frequency comes from the n squared, which is the vertical derivative term. That's the w d theta dz and the w ds dz. It's an explicit term in the temperature equation. You can't do this splitting in z-coordinates if you had written out the equations with advection. You have to have the temperature equations, temperature and salt equation as part of your baroclinic solver because of that vertical term, w to n squared. But here, because we have a Lagrangian in the vertical, we're capturing that dynamics, that n squared dynamics is being captured by the shallow water equations. And so now what we've got left to do is actually worry about what's missing, and that's horizontal transport along the layer. And so what we're going to do is we're going to integrate forward the baroclinic equations a few times, in this case, n times. And then, actually, it was m times, sorry, m times. And then we're going to add up all that transport, and then we're going to advect temperature and salinity with that. And that allows us to take longer time steps for the scalars, the tracers. And this is, again, a time-saving feature. It's particularly useful if you have a lot of tracers, and that means biogeochemistry. So if you have biogeochemistry and you have 30 species of, I'm not allowed to say bugs, so we'll say stuff, the interactive stuff, and chemistry and so on. If you've got a lot of these tracers, they end up being very expensive, and even more expensive if you're using the same baroclinic time step. So this gives you a huge savings in cost if you can subcycle the baroclinic dynamics relative to the tracers. And the last part of this is a part that Andrew's going to talk about, which is we've done everything here Lagrangianly in the vertical, and that can mean that your coordinate systems can become very distorted, and you have to reset those occasionally. And so there's going to be one step on the outside, and typically we actually only do one of these tracer steps per remap. We've always said we would do more, but well, life is finite. We only have a certain amount of time in the week to actually make these things work. So in principle, we could do this, but I think in practice, it's better to not do that. We want to do remapping in the vertical, which is analogous to vertical transport, actually, which is one reason why you might want to keep them together. But we do this remapping to reset the coordinates to something you might want. because they're drifting and becoming distorted. Okay, so that's the algorithm. The actual time stepping is actually very simple. Most of the time stepping is actually as easy as, I dare say, this is actually almost a swear word, Euler-Ford. There's good reasons for why we're actually doing that. Transport schemes can actually be made high order in time if you're upstreaming. And so it can be written as an Euler-Ford scheme, but it's upstreamed. And that gives you, you can actually show that you can get back accuracy in space and time if you do things right. So just because it's Euler-Ford for some terms does not make it necessarily inaccurate, although I wouldn't suggest that our time stepping scheme is high order at all, not yet. And then the other term is in the vertical direction, we often treat viscosity implicitly, viscosity and diffusion implicitly, and those are often done with an Euler backward step, which is also, but that's because we need these things to be stable, and we're using implicit viscosity in the vertical as a stabilizing scheme. But the one place where we're doing something a bit different is in the Coriolis terms and the momentum. This is the Backlinic system again, and I've got a continuity and a momentum equation. I've got continuity again and the momentum equation. And this is the Runge-Kutta, second order Runge-Kutta method, where we do a half step forward with your system. And then we then recalculate using that prediction, that guess, U star and an H star, in order to do a better estimate of what's happening in Coriolis. And the reason for that is Coriolis is explicit in this model. We'll see why it has to be explicit in this model later when we talk about horizontal spatial discretizations. But this is the only easy way to solve the Coriolis terms in our on a staggered grid to do it explicitly. Oh, hi, no. So this is the method we use, Runge-Kutta. There's actually various algorithms, optional algorithms. We have a third order Runge-Kutta. If we're fully explicit, we have a third order Runge-Kutta. But for the most part, we're using second order Runge-Kutta with barotropic splitting. And so this is just a way to stabilize a Coriolis term. Okay, so that's, here's a slide that's out of order. Now here's another time stepping thing. So remember I said Fing is for the most part Euler-Ford. Here's an example of that. This is the continuity equation. These are the fluxes in the continuity equation. I didn't actually write that out, but this is the, yeah, there it is. Yeah, H star is Hn, and then I've got a flux of mass. And this is, this expression on the top here is not Runge-Kutta in the sense I'm making a U star prediction at a half time step. This is a full prediction forward, step forward. But I'm only doing it in the X direction. So here we are, we're applying a one-dimensional flux calculation, which will be upstreamed and nonlinear, limited and so on. That's the F. And we're going to calculate that flux only in the X direction. And then we're going to update H. That's the H star. And then I'm going to calculate the fluxes in the Y direction. And I'm applying the same flux, but now in the alternative direction. And I calculate that flux. It's a function of V now. Take its divergence, and that gives me my new H. So Hn plus 1 has been obtained by 2 Euler-Ford steps. Okay, that's what I mean by, for the most part, we're doing Euler-Ford. You wouldn't normally do that for accuracy. And in this particular case, if we didn't do anything if we kept on doing X, then Y, this would truly be just first order in time. But if we change the order, so if in the next time, I'm going to make my Y step first to get my H star, and then I do the X. So first I did X then Y, next time I'm going to do Y then X. By alternating those directions, it turns out those first order errors, those splitting errors, actually cancel and you get a second order scheme. So this is actually a second order scheme, even though at the heart of it, we've got these Euler-Ford steps. So this alternating direction is called strand splitting to reduce the splitting error. And the fluxes are these nonlinear functions which are designed specifically to make sure that the quantity we care about is satisfying some constraints. In the case of continuity, we do not want the thickness to go negative, because that would be kind of weird. I mean, there would be less than zero stuff, it would be a negative stuff. So the way we do our transport scheme is we reconstruct from the mean values profiles within each cell of H, and we use, say, a third order scheme to do that. So we're using 3 points to calculate, or even more sometimes, to calculate this profile within the subgrid distribution within the cells. And then the flux is the area underneath that reconstruction. And so over here on the right, I'm showing you two cells labeled HI and labeled HI -1. And I've got a flow to the right. And the amount of stuff that I will have in the future in HI, the future HI, is basically what I lose to the right, which is the shaded tangerine color, plus the blue, light blue stuff coming from the left. And that's just area integrals. And you can show that if I ensure that the reconstruction everywhere is non-negative, so it's allowed to be 0, but it's not allowed to go negative, then of course the area under each of those curves will be non-negative, which means that the sum of my calculation of what's left behind, i.e. what I lost and what I gained, is also going to be non-negative. So by limiting the reconstruction, we can ensure that the future values will always be non-negative. So this is they call it reconstruction average and evolve methods. Basically, it's a transport scheme using these subgrid scale reconstructions. So that's why. So that limitation that H is not allowed to go negative introduces a nonlinearity. If I just wanted to use always third order reconstructions, i.e. parabolas, everywhere, and didn't do any limiting, this scheme would actually be considered linear. But it's the condition that we can't allow it to go negative that introduces nonlinearity. And it's for that reason that we have to be careful in the future as well about this is going to have an impact later on when we talk about the barotropic splitting. So this was continuity. H can't go negative. We also apply Easter's method to traces. So now I've got the tracer equation for theta, and you should notice that these equations look pretty similar. The only difference is that now I've got a theta instead of just an H, right? But I've got the same H appearing here that I had in the previous equations. And this is what we call a consistency requirement. H is evolving the same way that theta is, so that the total amount of stuff is always represented consistently. And it's the same idea. We do the X flux of tracers with a reconstruction of the tracer, and then we do the Y flux, and then we do the reverse for the subsequent time step. This time, the reconstructions of tracer, they also can be high order. And in fact, there's actually even very high order being added to the model. But right now we've got ppm, for example. But this time we might use a different constraint. So negative salinity doesn't make sense, but negative theta does, right? Because the freezing point of seawater is minus 1.8 or something. So positivity isn't the requirement you have. In this time, we're actually going to use conservation of extrema. So if you have a profile, you don't want to generate new extrema or new oscillations within a monotonic profile. So if you have a sequence of values on the large scale of your cells have monotonic values, you don't want new oscillations to appear. That's called monotonicity, a monotonicity constraint. So what we do is we apply a limiter that satisfies that non-oscillatory constraint. And so this is, again, a nonlinear flux because of the limiters. But it's exactly the same as the thickness equation, as you just saw. So that's transport in the horizontal. Remember, transport was along these layers, which are in between these surfaces of general R. In the algorithm I showed you that we're subcycling the barotropic equations. And this is just a quick, I will have to confess, this splitting of the barotropic and baroclinic has been, also, just like the pressure gradient error, has been a long-standing issue. How to split the equations of barotropic and baroclinic has also been a very long evolution. And I would say that we are still making tweaks to these algorithms to deal with issues. So there's no final word on any of this. If anyone wants to just get into hardcore numerics and write some papers on this, there's plenty of things to do. But this in a nutshell how it's going to work. The pressure gradient along a surface has two contributions. It has a baroclinic part, which you might just say is the part if I start at the surface and integrate down my pressure, my density anomalies, then that gives me a pressure. And then there's a part from the displacement of the surface itself, and that's the kind of G gradator. Okay, so if the sea surface goes up, you have pressure increase below it, right? So that's like the surface contribution to the pressure gradient. So we're going to try and split out that part. And if over here in the momentum equation, just below, after the second point, you'll see that I've separated out the baroclinic pressure and the surface pressure gradient, G gradator, okay? Now, the other thing we're interested in is kind of how does that surface evolve? And that surface is given by the evolution of the sum of the thicknesses. So if each of these layers can have a little divergence between them, but if you stack them all up, that gives you the net divergence, and that's what's going to change the sea level position. So this equation for eta connects all the layers, and if you take the layer equations and stack them up, you'll arrive at this d eta equation, which is basically can be written as the divergence of the depth integrated flow or depth times the average flow, okay? Vertical average flow. The equation for the vertical average flow can be obtained from this baroclinic equation by vertically averaging it. And if angle brackets here is now going to refer to depth average. And so the depth average evolution of this equation is the depth average of the accelerations G, which are all of the terms I'm not writing out, depth average of the baroclinic pressure gradient, and the depth average of G eta, or eta is just the surface gradient, or surface field. It's the same, it's seen the same way for all layers below it, so there isn't an averaging to do there. And so now I have equations for the average horizontal flow and the sea surface height, and that's the single layer shallow water equation. So we can step that forward with a small time step, as we talked about earlier. I've labeled that with a T prime for convenience. Over there, you can see how we're subcycling. Delta T prime is small compared to delta T. And then the final update over here is I take my update equation. I've symbolically represented the accelerations from the du dk equation, which is all the terms. I'm going to subtract out the part that belonged to the barotropic. So that's the d by dt of eta, so d by dt of u bracket, evaluated at n, so that's the explicit part. And I can substitute back in the average of those accelerations from my barotropic subcycling. It's symbolically, that's how we do it. The details are so much more complicated, but that is effectively what we're going to do, okay? This has actually been used in many different models, just like this basic concept, and we're basically using the same idea here. So that gets us an evolution of the momentum equations, but there is a slight problem, which is I actually have two equations now for the sea surface height. One of them, remember, we've got this baroclinic H equation layer by layer. If I add them up, I'm going to get one estimate of eta, sea surface height. But I've also integrated forward my barotropic equation with a small time step. And remember, F, I made this point earlier, is nonlinear. And so this nonlinearity is going to make it very hard for these to ever have the same result. We can show that if it is linear, that they can have the same result. So that's one thing. So if we can make the nonlinearity small, then we're in a good place. We're only making small errors, but in practice, these are not going to give you the same answer. So basically, we have a problem, which is that the sum of F in the vertical is not going to be equal to the barotropic time average horizontal transport. Okay, so there's a not equal sign there. And this is something that we do to solve that problem. There have been many attempts to solve this problem. This is what we're doing, is we are going to introduce a vertically uniform delta big U, okay, and we're going to add it only in the layer equations, and we're going to write down the constraint that delta U is such that the sum of F equals the barotropic transport. It is only changing the velocities in the layers in the estimate of the transport itself. It is not an update or a new term in the accelerations. It's just changing the estimate of f. So remember, f was calculated by making these reconstructions. So we're making these reconstructions, and we're saying, we're going to apply some limiters, and we're going to say this is, at this point here, it's third order accurate, and with the limiter, it's a little bit less, and so on. So we're making these somewhat ad hoc choices about how to reconstruct. If I had, say, switched to a second order scheme or a fourth order scheme, all I'm doing is changing h's, and that changes the result of evaluating f in that integral. To that extent, adding a small delta u here is in that class of making adjustments to that reconstruction. What that reconstruction change is, I couldn't tell you, but it's in the same place in the code. That's what we're doing. We're just changing the way that we numerically evaluated that integral. And so if delta u is relatively small, turns out it is, in the paper we showed that it is, then this is just no different to making a slightly different change to the numerical truncation. And so even though we're kind of solving for this average vertical flow delta, and there's no corresponding physical equation or term in the momentum equation or anything like that, it seems to be consistent, physically consistent, in the sense that the numerics have these truncation errors. And again, if f was linear, we can show that delta u in the solution would be 0. So if you're in a situation where you have no limiters acting, delta u is 0. Okay, so we've covered a lot of, done some numerics on the vertical, discretization on the vertical, so now we're going to move to the horizontal. And I've alluded to this already, but to say it explicitly now, we stagger variables in the form of an Arakawa secret. Has everyone here heard of Arakawa? Who hasn't heard of Arakawa? Don't be shy. Arakawa is, I think he's still a professor at UCLA, and he was like the grandfather, along with a few other famous people like Sidoni and so on, of numerical methods in the atmosphere. He actually also built, did you know this, Frank? He actually built an ocean model. Did you know that? At UCLA, yeah. Around the same time that Cox and Bryan were working, but he ended up focusing on the atmosphere. There was this famous report, the WCRP report, where everybody was struggling to build global models, and they got together and wrote down the fundamental numerics of atmospheric models, how to make atmospheric models work. And it's basically the go-to report. It's a tech report from WCRP back in the 70s, and that's where we all get our nomenclature from, our symbology for delta x's and our labeling for grids. The Arakawa C grid is dictated here, shown here, illustrated here. The orange dots are what we refer to H points in MOM6. That's where we carry forward the thickness, the temperature, and the salinity, and also pressure, if you're thinking about it as a sort of scalar variable. And then in the horizontal direction, we have a grid where we've drawn these lines which describe finite volumes, and it's the flow across those edges, which are the velocity components, and we have the u point staggered to the east, and the meridional v point staggered to the north. And this is very natural for the representation of the divergence of flow, also very natural for the representing the divergence of scalars, transporter scalars. And I've also labeled on here in diamonds the Q point, which is a natural location, given where V and U are, a natural location for the vorticity, and therefore also potential vorticity. So that's why we label it the Q point. The challenge with this staggering, and this is actually one of the things which was in this famous report, is that it's not natural to evaluate the Coriolis terms. So the Coriolis term, the linear part of it looks like du dt is an FV, but FV and U are not in the same locations on this grid. And you can see that I have to do a horizontal average in both X and Y of the V point to get it to the U point, and vice versa. And this is just one particular choice of discretization. It's very important that although these operators are linear, that the behavior of these schemes are very different. I'm averaging in X first to get the V at the Q point, multiplying by F, which implies that f is at the Q point. And then I'm doing an average in the y direction to get that term to the U point. You could have done it a different way. You could have said, let's go via the orange points, in which case I would have swapped those x's and y's in that expression. And that gives you a different scheme. It gives you a different scheme in particular. Is that microphone on? Or is it just echoes? That particular, changing those orders of how you do the averaging matters for its properties, for example, of PV conservation or energy conservation. Energy conservation was the big thing that everyone was going for in the atmosphere, and it's not irrelevant to what we're doing here. One of the problems with this averaging is that it can filter the state. And if you're filtering the state, when I say filter, I kind of just mean smoothing, for example. The problem with smoothing or filtering is it means that there's information being lost. And in this case, with the very simple 2-point averages, which are that's what that bar X means, 2-point averages actually supports a computational mode. +1 and a -1 structure, as illustrated here in V. I've got velocities going up, and the next row of velocity going down, up, down. If I take a 2-point average of that to the Q point, I get 0. So this is called a computational mode because it can't be felt. So the horizontal accelerations in the x direction are unchanged by the fact that the velocity in the north and south direction is huge, but it's doing this, up, down, up, down, up, down. So it's a computational mode because there's nothing to feed back on it. There's nothing to undo it. There's nothing to constrain it, okay? So this is the problem with the Arakawa C grid. There is no perfect grid, it turns out. All of the possible staggerings you have in the horizontal have something that's not quite right. We won't go into that because MOM6 is only on a C grid. But the consequence is that there is a problem for the high frequency, the short scale inertial oscillations, where we don't see the Coriolis parameter at full strength at the grid scale. And this is something that you should watch out for in solutions. This is one reason why we use parameterization to do a strong job of filtering at the grid scale. But you will recognize this problem happening if you see coherent lines or checkerboarding of velocity in your solutions. It means you need to add some viscosity to remove those. Okay, this is a figure just to introduce something I think is relevant to regional models. Of course, open boundary conditions. I think Kate and Fred can talk about this in more detail, so I shall not dwell on it too much. I just want to say one thing about it. Maybe stop me if I start saying what you're going to say. But this diagram I love. Kate came and visited us at GFDR in 2016, and we brainstormed, what would we like in a model that was able to do regional problems? And we were just drawing out how would we set up something that was truly flexible and we could do any problem we would want. And rather than just doing the old-fashioned thing of, let's just say the outer side of our domain, our square rectangular domain, is an open boundary. Let's do something a bit more useful. And boy, did we make a mess of it. I mean, it's so, it's a great vision. We're going for absolute flexibility, but it's been very, very hard to actually pull it all together. But it works. And so thanks to Kate and Enrique and all of the regional people here working on this. It's been a long development, but it's actually, I think, a capability that we're going to find is another reason that MOM6 is going to be useful. The thing I wanted to highlight, and maybe, are you talking about ghost cells versus non-ghost cells? Yes. No? Good, good. I haven't wasted a slide. The conventional way of implementing open boundary conditions in ocean models was to use this concept of ghost points. And I've drawn here the corner of a rectangular domain where we would say, we've got this big array, and we're simply going to populate the edges of that array, which are outside of my domain, with values which are consistent with my boundary conditions. So for example, if I wanted to have transport of temperature in from the west here, I would set these red values to be that temperature I wanted vectored in, okay? And it's simple, it works. Except if I wanted to do something slightly different, like say, I want to transport in temperature with this, but I don't want the diffusive flux to have that temperature because I want to have a different condition on diffusion, such as no diffusion. There's an inconsistency there, and you've got one value to do it with. So that's just an example of the limitations of the ghost point approach. A bigger limitation is that when we had our vision of trying to put open boundaries anywhere in our domain, one of them was that we could have acute outside joining of open boundaries. So instead of having a rectangular open boundary zone on the outside of your rectangle, you could have inner corners where you've got, say, I don't know, who could imagine why we do this, but you could have open boundaries intersect in this fashion here, and then they would be sharing, the northward flow in the center there and the eastward flow in the center there would be sharing an upstream point. So not only did I have a problem with underspecifying the problem with the ghost points on this cell, on this boundary, over there I've got a bit more fold because I've got fluxes in different directions trying to use the same value. So what we do instead, and this is one reason why it's been a very long implementation process, is we've said we're going to take every single term and give it a range of choices, options, as to how it's specified. It could be using just a data value from upstream, or you could be specifying something like a no gradient or a no vorticity value or whatever. So that every term has been looked at individually, has its own set of flags. And so in this case, I can specify the transport, the properties being vectored on by transport at the northward points on that corner and on the eastward sets on this corner independently. So each term has its own set of values, including transport versus diffusion and so on and so on. In viscosity in particular, this matters because viscosity shares stresses at the Q points. And if we want to have different boundary conditions for different boundaries, for example, eastern boundaries and western boundaries don't behave the same way as north. So we can. It's very, very configurable. And so that's one reason we chose this approach. I'm running out of time, which is good, because I have just left a few bits and pieces, which I put in just to fill the time, and with 3 minutes, I will probably fill them in. One thing I just wanted to comment on, I mentioned that we stagger things to the east and north. This is called a northeast convention. It's something you should get used to. It's actually not a choice we made. It's a choice as a result of FMS. Stand up and round of applause. We have Jeff at the back there wrote FMS when he was at GFDL. This is a choice. It was a very important choice because we were using what we called a tripolar grid, and we needed to have values on the northern edge of the kind of latitudinal part of this that would represent structures when you fold things over on the tripolar grid. But I'm not going to get into it. But you couldn't do that if you use the other conventions. So this is why this convention was chosen to be able to support global tripolar grids. But it's important because you need to know which side things are. U is always to the east, V is always to the north. And in the code, we use a soft convention to help us as developers, so it's easier to read the code. We use capitalization of I to mean I plus a half. Very convenient. It is actually in the documentation, but no one ever reads it. But it actually, when you realize that, it makes life so much easier to read the code because you say, oh, that's I plus a half or I minus a half, right? I minus 1 plus a half is I minus a half. So that's one thing. I'd like to, something we don't normally focus on, but it's extremely useful if you start writing code or looking at the code. MOM6 religiously preserves answers. This can be a nightmare for some people. It can get in the way of collaboration, but it's actually not hard. The reason is that we've had a long history of needing, to be able to recover solutions which we've been running maybe 10 years ago. You can run a climate model at great expense, for example, the pop 10th degree, and then you might have not made the diagnostics you needed, and you need to go back and make the diagnostics. But if the solution changed, the diagnosis of that new term is not going to match. And you basically have to throw away the old data set and make a whole new data set. This is one advantage. It has other advantages as well. We've been religious about it to the point of being notorious. But as a result, in order to do this, we also recognize that we need to fix bugs and make the code better, faster, and so on. And so in order to allow this to happen, the code has this growing list of what we call bug fix flags and answer date flags. And it can be very confusing if your code is happily working away one day and the next day you've got an update and all of a sudden you're getting different answers. To support that, we have what we call a default answer date. And if you take the model at any particular point in time, I highly recommend that you set that answer date flag to the day that you first run your model. And what it means is, as we fix bugs, add new schemes, and make choices for you, you'll be using the choices that we made on the day that you checked out the code and not inheriting this changing model where we're pulling out the rug from under your feet. Just a pointer to help you deal with that. One other thing, it's related to the answers, is that this is something that I think most models now do, but incredibly, how should I put this politely? Just a few years ago, this was not the case for other models, that we expect the parallelization, which from our point of view is purely an infrastructure thing. It's the computer, right? Should not change the answers. By that we mean if you were to decompose with, say, 6 processes, and you did this parallelization with 6 processes where you had them in north-south stripes, and you changed using 4 processes in east-west stripes, the solution should be independent because it's just the choice of how you put it onto the computer. It's not a change in the choice of discretization or the equations or the physics or anything else, right? It's an absolute requirement. FMS provided the frameworks to do this, and it's something which is tested rigorously in any change of the code we now do is we make sure that the code is able to reproduce across processes. Similarly, restarts. And again, to my surprise, just a few years ago, there were models that did not reproduce across restarts. But this is absolutely essential when you have a finite queue time. If your model takes a week to run and your queue only has a 12-hour queue, you have to stop the model and restart it. And if you've got a different answer than if you had run it for a week at once, then what kind of science are you doing, right? So this is another reproducibility requirement. We have other constraints on the code that we are also notoriously religious about, but these are the 2 big ones. If you violate these, there's something very wrong. But it turns out we've also got a lot of tools to help you actually figure out what's going wrong when you're adding code to solve these problems. And then the last thing I wanted to just quickly mention, I'm over time now, 2 minutes in. We are moving towards newer methods. So this is a recent piece of work from Wenda Zhang, paper submitted to James, where we have replaced that 3rd order PPM reconstruction for continuity and for potential vorticity, the linear interpolation for potential vorticity with a 7th order. I mean, 7th is amazing, way up there. 7th order Wiener scheme. And the reason we did this was because the vorticity dynamics, which matter when you start resolving the deformation scale and getting into regional scales, really changes the amount of energy you get. So this is using the conventional linear Arakawa type schemes. On the right is using the 7th order Reno, and this is what it should look like if you had much higher resolution. You'll see the level of energy, this is vorticity we're looking at, much closer to the high resolution model. And in fact, if you look at the spectra, the blue is the high resolution spectra, and the orange is what you get with the Arakawa scheme because it's dissipative by necessity to keep it stable, and the green one is much closer to the high resolution one. So that's a win. So this is for vorticity. There's a group at University of South Florida working with Alan Woolcraft and Eric Chazanier, implementing this for traces. We're trying to make the model higher order, and I think the regional community is probably going to be an application where that's going to make a big difference. And this is my last slide. I'm going to not talk much further because I know that I just noticed in the schedule that you've got discussion about analysis, but analysis is the reason we build models. We need to actually understand what they're doing. One comment about the general coordinates is it makes life harder, but we allow the model to be diagnosed in alternative coordinates, so you can do your diagnostics in whatever coordinate you like. And there's plenty of material out there to refer to. Okay, I'm 4 minutes over, so we've got coffee waiting for us. So either have no questions or be quick with your questions. Thank you very much.
We have time for one or two questions.
Real quick, when you were talking about the subcycling of the barotropic, baroclinic, and tracers, you said that the tracers step at a slower time scale than your baroclinic.
Yeah.
How do you determine what that time scale separation is? Is that sort of
That's a very good and open question. Sometimes trial and error.
We have typically assumed that you want to be at a current number for this time step of around 0.1 at most, so that you're not hitting those other limiters we have where we model against CFL. So don't go above 0.1 or ever for the transport of tracers. But how much finer you can have the baroclinic is an open question at this point. If it's too fine, if there's too disparate of it, you might have a very big errors being introduced from this splitting, because there is a splitting error, a subcycling error, sorry. So the answer is trial and error. One thing we have noticed is that we've been using setups where we thought we were safe, but then when we made a change in that ratio, the solution did depend, and that's a bad thing. So we back off. We want to have that ratio closer to 1 than to high, such that the solution doesn't depend on that very strongly. It's one of those things right now where it depends on how nonlinear the flow is, I think. Because if you have a lot of eddying motions going on in your continuity solver, you're going to be averaging over those in terms of horizontal transport when you put them into the tracers, and so you're missing stuff. So if you've got high curvature flows evolving very rapidly, probably you should have a very low ratio. But if you've got very smooth, very large, slowly evolving systems, then you can probably get away with a lot.
Was there another?
Yeah, I was wondering why when you said a couple of years ago when you do the restart, that's going to give you a different result every time. Why?
Because people didn't save all the terms which were lagged in time. So, one would argue,
One would assume, the way I would rather the model only had its state variables in the restart file. So velocity, thickness, TNS, right? But there are plenty of, the time stepping I outlined is actually a lot more complicated and, is very simple compared to what we actually have. There are many schemes which are expensive, and having a guess for their iterative solution is helpful, for example. So you would, whatever the inputs to those schemes are, you might also add to the restart file. And so if you add some sort of time filtering to your model, for example, the title of components have these extra bits and pieces in them, for example, you have to add them to the restart file. Otherwise, you won't be able to calculate exactly the same value when you do a restart. So
it's just that there are, in time, other dependencies across that time value being added.
Right, just because the time step you remember is staggered, there's some short time steps and very long time steps.
Yeah.
You just have to save everything at that.
Yeah, so for example, for
dynamic solver, I showed it as just being subcycling forward, but in fact, it involves an average from before. Just for stability, there's a paper by Shepetkin about how to do this. So yeah, even the dynamics has these dependencies across that time boundary. In principle, I agree. It really should just be the state variables that should be in there. But for efficiency, we have to add other things there because the time stepping otherwise gets more complicated to make it accurate or stable.
Okay, I think we should move to topic.
Excellent, thank you. We'll reconvene at 11:05. I'll ring the bell.